Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully, you guys are doing okay. Good to see you. Appreciate if you have your cameras on, if possible. Let's actually jump into it. So we're actually going to start calculus today. I don't know how far we're going to get, probably not very far, because I actually want to talk a little bit about what calculus is before that. And also we have just something very small to wrap up from the last section also. So let's actually get to that. Let's make sure I can see the chat, and let's get into it. So one more thing to wrap up. And this is called average rate of change. Okay, so let f of x be a function defined on, at least, could be more, AB. Okay, so this is an interval, right? Some range of x values on the x-axis. Interval. The average rate of change of f of x on AB is given by so average rate of change. We usually don't have like a symbol for this. So this is going to be given by f of b minus f of a over b minus a. And of course, you'd recognize that as one of the versions of the difference quotient, which it is. And essentially, this is also called the average rate of change. Now, what this is the slope of the line. Let's call it straight line, to be specific, connecting points A and B. So A, f of A, and B, f of B. Such a line is called a secant line. So essentially, what you have is here's your x-axis, here's your y-axis, and here is, your function doing what? Doing as it do. This is your f of x. And let's say A is somewhere here, A, and B is somewhere over here, B. And my function is defined on that interval. So pretty much what I do is, well, here's a point here. That is f of B, f of A, sorry, f of A. And then, of course, that's the point on the function there. That is your f of B. And essentially what I do, or what we do, is we connect it with a straight line. This is called the secant line. Okay. And now the slope of that line is going to be what the average rate of change is defined to be. So how do we get that? Well, I want different colors here. I don't know. I use so many colors already. So if I call this, x1, so that corresponding value is y1, and I call this guy x2, so the corresponding value is y2, then the slope of the secant line let's call it m sub secant, is given by y2 minus y1 over x2 minus x1. And so that's just going to be f of b minus f of a over b minus a, right? So that's where the difference quotient comes from. It's actually a slope, right? And that slope actually will give you some information on how this thing is changing on average. And I'll kind of give you the interpretation later. But I should also mention, we can also change notation. So sometimes we want to describe it in terms of the original point and a point that is some distance from the original point. So sometimes instead of a, we will call it x, and then the second value we'll call it like x plus h, right? So it's x, and then there's a second value that is a distance h away. And we measure it using this notation. So go here. This is going to be called f of x. And of course, go here. This is, of course, f of x plus h. And again, there's this straight line connecting the two guys. And so now, when we go the slope of the secant line, we get y2 minus y1 over x2 minus x1. And this just becomes f of x plus h minus f of x. x2 is x plus h, and x1 is just x. So of course your x's cancel because you have x minus x. And so this gives you f of x plus h minus f of x over h. And that's the other form of the difference quotient that we're used to. So the difference quotient isn't some random expression. It's actually a very specific expression. And it's not at all a strange expression. It's just the slope of a straight line. And we'll kind of get into why is finding the slope of a straight line so important. But we'll get there pretty soon. But so far, the difference quotient, or the slope of this straight line called the secant line, is referred to as the average rate of change. And why it's called that is the numerical value that you can get from it can be interpreted as how much the output changes per unit change of the input on average over some interval, right? So you can't tell directly how much it's changing. It can change more sometimes or less sometimes. But just on average, how much does it change overall for every unit change? And we're going to see that pretty soon with an example. I'll also just mention that when concerned with average rate of change, the the AB notation, that's not an official term, that's just what I'm calling it. AB notation, right? Not the one with H, is used more commonly, right? So whenever I ask you in general, average rate of change of this and this, people usually just call it A and B. You don't want to call it like the first point and then the second point that is a distance h from the first point. No, you just want to know what the points are. You just usually call them A and B, and you use that A and B, right? The difference quotient in this form is used in other contexts, which we'll get to those contexts later. But they are equivalent. So technically, if your A is X, then your B would be the X plus H. But then you'd have to think of your B in terms of being A plus a little bit. And it's just too confusing. It's just too much gymnastics for this context. So we usually just use the AB notation in the average rate of change context. So I'll talk about the interpretation after an example. Here's an example. Suppose f of x equals, let's make it 4 minus x squared. Find the average rate of change of f of x on, and I'll give you an interval, 1, 3. I could also have said, I could say 4 minus 1 less than or equal to x less than or equal to 3. So I could use interval notation or inequality notation, means the same thing. Don't get confused. Okay, so that's the problem. Average rate of change, straightforward. Normally, if I ask you about average rate of change, it's going to be something that's straightforward like this. So it's not going to be like some huge complicated word problem where you have to figure it out. I just straightforward ask you average rate of change, find it. And I expect you to know, oh, I just use the difference quotient. So here, your AB is just the minus 1, 3, right? So the minus 1 is the A, the 3 is the B. And then you're going to plug that into this formula. It's going to be f of B minus f of A over B minus A. Pro tip, you have a formula, you need to get it memorized, which in this class is all of them. Like I expect you to memorize all the formulas that I give you. Every time you want to use the formula, just write it down, right? Eventually you'd write it down so much that you automatically forget it. You'd write it down so much that your hand will remember it even when your brain forgets. It literally becomes muscle memory. A lot of math is like that, by the way. A lot of times when you see someone who's like, they appear naturally good at math, that they just catch things and they're very quick to do something. And if they make a mistake, they're very easily catch it. It's because they've done so much math that it's muscle memory. They can literally feel when their hand writes the wrong thing. That's the level you want to get to. But that would be it. And so what this basically means is we need to compute f of 3 minus f of minus 1 over 3 minus a minus 1. And that's all we're going to do. And just remember what f of 3 is. You go to the original f of x, you plug in x equals 3, and that's what you're going to do. So f of 3 is going to be 4 minus 3 squared. I don't need to put brackets around the 3 because PEMDAS would tell you that you want to do the square first. But you could put brackets around the 3 if you wanted. You could have done that, or you could have done this. It wouldn't be wrong. So the thing with parentheses is, if you're not sure, probably use them. Better safe than sorry. It's never wrong to overuse them unless you're putting the wrong things inside. But you can be wrong if you underuse them. So even though it's not terribly necessary, you could do it if you want, and nothing would be wrong. 4 minus 1 squared. Notice that here I did put the parentheses because I want to emphasize that the minus 1 is being squared. And so it doesn't affect that negative in the middle. You don't want to get into the situation where you think you have to add the 1 instead of subtract the 1, which if you remove the parentheses, that's what you're saying. Because then it's like you minus a minus 1 squared, right? Which means plus 1 squared, which is not true. Okay, 3 minus a minus 1 gives us 4. So then we just calculate this. So this is 4 minus 9, that's minus 5, minus 4 minus 1, that's 3. So that becomes minus 8 over 4, or minus 2. And that's the average rate of change, right? So here's how we get that interpretation. Okay, so here's what that minus 2 means. It means on average, on the interval minus 1, 3, f of x decreases, and that decreases is because of the negative sign, right? If it was positive, you would interpret it as increase. Decreases by 2 units for every 1 unit increase in x. So the idea is every time our x value increases by 1 unit, our y value will decrease by 2 units. And it's not always the same. It's not always that fact, but on average over the period that we care about, right? So you'll notice that in this example, right, 4 minus x squared is like a parabola. Let me just be consistent and draw the graph in red. It'll hit here at 2 and here at minus 2. And we care about the interval minus 1 to 3. Let's put that there. And so maybe I should extend this a little bit more. So 1, have it here. And of course, right there, our y value was 3. 3 hits here. And our y value at this point is minus 5. Right? And so now what are we saying? If you connected these with a straight line and measure the slope, you'll end up getting that the slope is minus 2. Now, what does that mean? Basically, it means you'll notice that in this time period, notice x increased by 4 units, right? My x values went from minus 1 to 3. How much increase was that? I added 4 units, right? Minus 1 plus 4 gives me 3. So my x increased by 4 units. In that same span of time, if I were to look at what happened with the y value decreased by how many units? Well, the y value was 3 and now it's at minus 5. It decreased by 8 units, right? So y started at 3 and y ended at minus 5. Okay, sorry about that. I got cut off for a second. Is everyone with me? Can you hear me?
Yes.
Yep.
Okay, and I can hear you. All right. So sorry about that. So where were we? Okay, hopefully you're seeing that. Okay, so notice that in this time period that we're talking about, my X value increased by 4 units, whereas my Y value decreased by 8 units. What you'll notice is that for each, notice that Y fell twice as much as X increased. So for every 1 unit increase in X, Y lost 2 units. And on average is the important part. So in the interim, this might not be true, right? Because if you look, for example, on this interval right here, right? As your X increased, your Y value also increased. Your Y went from 3 to 4. So in this little window here, your Y value actually increased. So it can increase and decrease and do whatever it's doing in the interim. But the idea is, on average, over this entire period, how did the Y value behave? On average, it was decreasing. Most of the time, it was decreasing. It may have increased here and there, but overall, the trend was a decreasing trend. And so that's what the average rate of change is telling you. And hopefully that's clear. Is that clear to everyone? We get what I'm saying? Okay.
Yes.
So that's average rate of change. And how you compute it? You basically take the slope between the 2 points, right? That's the formula. Okay. Now, like I said, this is a very simple example in the sense that nothing crazy. I'm using a formula you're all aware of and all of that. But we're actually going to build on this concept later on. The fact that we can actually use the slope of a line to talk about how things change on average in relation to each other is actually what is responsible for half of calculus, believe it or not. That simple idea. So it's worth kind of elaborating a little bit on it, even though average rate of change in general is not going to be a big deal for us. There's another kind of rate of change that is going to be a big deal, but that's the average rate of change. That's that. And that kind of wraps up the preliminary stuff. So at this point, as I mentioned, I do expect you guys to be awesome at just like algebra and pre-calculus. And I reviewed exponentials and logarithms with you guys because it just, statistically speaking, students aren't as awesome at those as they should be. And so it's just worth me going over them. And now we're kind of starting into the calculus part of the course, but the concept of average rate of change is going to be important to understand the concepts later. So now we're going to start calculus. Yay! So excited. And without further ado, is this a U or an O? I don't remember. Yeah, not an English teacher, it doesn't matter. So without further ado, let's talk calculus. Okay, so calculus officially begins now. All right, so before we start jumping in and I start telling you about the mathematics of calculus and what we're going to do, and here are these formulas, here's what this is, here's what this is, just want to talk about what calculus is and why it's useful. Because it turns out that a lot of people just don't know. Even people who do calculus. Yeah, calculus was this thing I do in school that I never used in my life. I think it's kind of useless. Yeah, those people are wrong. They're just wrong. Anyone who tells you that calculus doesn't matter in their life, they are wrong automatically. If you live in any scenario where technology is used, calculus is relevant to you. And if you're not using it, it's being used on you for sure. So I guess a cutting edge example, since I want to be current and show you that I'm hip and I'm not just some old man. AI, artificial intelligence. It turns out what artificial intelligence actually is. Yes, it's based on computer science, and that's how you plot it. But really, what an artificial intelligence is from my phone here because I keep hearing the ringing in my head when they call. Oh, God, messed up my flow. All right, so let's look at AI as a very sophisticated example. What an AI is, what an artificial intelligence is essentially a computer program who knows how to collect statistics, perform probability calculations on those statistics, and then use calculus to fit it to human behavior. Pretty much, right? Calculus is going to be the last leg of an artificial intelligence's thinking process, right? So you use a cell phone, you use calculus. Or more specifically, calculus is used on you to track you, to know what ads to show you, to suggest things to you. Calculus is a part of that process, right? So essentially, calculus is going to measure change, essentially, and differences, and just how different what the artificial intelligence thinks you want to know is compared to what you actually want to know. That measurement is actually done by calculus, okay? And it's done by using the calculus in the context of it knowing certain statistics and probabilities. And for that, you need data, which is why data collection and privacy is such a big deal. Because once you have that data, you can use a computer program to predict things about who's using that data. And the prediction, how good they are, how you can measure how good the prediction is, calculus. That's how you measure how good the prediction is. How you come up with an initial prediction, statistics and probability. Okay, so that's just one example, and that's a far out there example. There are many other examples which hit more close to home if you're a scientist. If you're a scientist, calculus is being used somewhere in the science that you're doing. A lot of you will use statistics and probability straight up front in your science classes, but you have to realize there are a lot of things in probability and statistics that you wouldn't know how to do if it wasn't for calculus. Have you ever did a scatter plot and tried to find a regression line? Do you know why we know the formula for a regression line? Calculus. In fact, high-level calculus, calculus 3. If we didn't have calculus 3, you would not know how to create a best fit line. Calculus is how you know to measure that. So even when you're like, you know what, well, calculus is useless. I kind of use statistics in my life. Dude, when you're using statistics, you are using calculus. Most of your statistics formula, we know those formulas because of calculus. Now in statistics class, they don't tell you this. They just say, here's the formula. But where did that formula come from? Calculus. It came from calculus 3, chances are. So calculus is useful. And if you understand calculus, it gives you potential to be on a higher plane than the average person in a real way. So if you never use calculus and you don't think it's useful, it's kind of your fault. It means you're not really paying attention. But let's pan out a little bit more and kind of talk about, in general, what calculus is. Let's not worry about the applications in real life. I'll mention a few, and we'll do some because this is applied calculus. But the examples in this class aren't going to be anything like awe-inspiring. But trust me, calculus is used to do some really awe-inspiring things in real life. We're not going to appreciate all that. I'll mention it sometimes, but let's pull back and talk about what is calculus actually studying. Like if you wanted to know, calculus is the study of what? Right? Like what would you say? Like if someone said, oh, I took calculus this semester. Oh, what is that? What would you say? Like when you say I took calculus, what would you say? Does anyone have an idea of what it is? Did anyone take it before and kind of know, you think you know what calculus is, what you're actually studying when you study calculus? Any guesses, any ideas? Let's talk about what is calculus.
Change.
You're studying change. That is true. That is also kind of vague, though, because a lot of mathematics study change. You can think of statistics as studying change also. And yes, I mentioned that you do use it. A lot of things study change. What kind of change? Or how are we studying change?
Continuous change.
That is somewhat true. But then again, continuous is a very specific word. It actually has a mathematical meaning. So I want to make sure you know what you mean when you're saying continuous. But yeah, half of calculus, not all of it, is about the study of measuring rates of change, right? So it's not just about measuring change, it's all about measuring how fast change happens. So it's not just about, oh, things change. It's about how long does it take things to change from this point to that point, right? So yeah, life is about change. Life changes all the time. Nothing ever stays the same. But calculus is what gives you the power to determine here's how long it's going to change from this situation to this situation, therefore I can predict, right? So life is about change. You know, the tide comes in, the tide goes out. But if you want to measure how long do I have before the tide raises from this sea level to that sea level, now you're studying calculus, right? Now you can know, oh, I have to predict. I have to basically predict what the sea level is going to be, and that's going to determine when do I go fishing, how high do I have to build this dock, right? You can determine a lot of things by knowing how fast the change happens. Change is happening all the time, all around. Knowing how fast it happens gives us a lot of predictive power. It gives us ability to actually make plans. So calculus is about not just change, but rates of change, how fast the change happens. And that is what half of calculus is about. So let's actually break it down. So let's break it down in terms of the math stuff that we're going to study. Calculus is the study of, you can think of rates of change as the main application. Like by studying these things, I would be able to predict how fast something is changing. Does anyone know what those things are? Like what are the actual things called that we study in calculus? What are some things that you study in calculus? If anyone did calculus before, what were some of the things you studied? Did anyone do calculus before, or are you all new to calculus?
I did like limits.
Limits? Yeah, limits. Right? Derivatives. And in fact, limits is an interesting one. I'll get back to it. But most people, derivatives would be the main thing that they remember from studying calculus. What else do you remember from studying calculus? Did you guys remember something called integrals? Right? So calculus is a study of derivatives, integrals, and their applications. That's what calculus is about. This is the study. We're studying these objects called derivatives, we're studying objects called integrals, and we're studying how we can apply these things to real-world applications. Now, the application that I spoke about earlier, rate of change, that's what the derivative is used to study. Integrals are used to study something else, right? So that's in a phrase. That's if you wanted to concisely say what calculus is about in a phrase, that's what it's about: derivatives, integrals, and their applications. When I'm studying calculus, that's what you're studying. In a word, right? Someone puts a gun to your head and says, tell me what calculus is about in one word, right? If you're given one word to answer this question, what is calculus the study of? Limits would be the answer, right? So we already mentioned limits, but calculus is all about limits. Like that's what it's about. It's just that the derivative is a special limit. It's a special kind of limit. The integral is also a special kind of limit. So while calculus is about derivatives and integrals, these are both types of limits, right? So calculus ultimately is just the study of limits. We're going to invent this object called a limit, and we're going to study it. And then we're going to want to apply this in a specific way, and we're going to use the limit to develop this thing called the derivative. And then we're going to want to study something else, and then we're going to use the limit to develop this thing called the integral. And then once we've developed these things, we just use that, right? So from that, once we use the limit to invent these things, we now just study those things, right? So these things are called derivatives and integrals, but we ultimately invented them based on the concept of limits. So in one word, calculus is the study of limits. If you had to say a phrase, calculus is the study of derivatives and integrals and their applications. Now, why is it actually useful? So it breaks off into two branches, right? So one branch of calculus is called differential calculus. This is the study of derivatives and their applications. Okay, then we have integral calculus. And this is the study of integrals and their applications. Okay, so yeah, calculus is the study of basically two kind of objects that were both developed from this concept called limits. It breaks off into two branches. There's differential calculus, where we study this thing called the derivative, and there's integral calculus, where we study this thing called the integral. Now, you might wonder, what is a derivative, what is an integral, and why do we study them? So here's what the derivative is about. The derivative is the solution, or I should say is a solution. It's a very sophisticated solution. One of the most useful solution is a highly useful solution to its so-called rate problem, right? So essentially, this is the study of rates of change. How fast do things change? Right? So like I mentioned, things are always changing in life, right? Tide comes in, tide comes out, sun rises, sun sets, crops grow, there's a harvest, you cut them down, they eventually grow again. Change is continually happening. Now, as human beings, for survival, we need to have control over our environment somewhat. We want to predict when changes are going to happen so that we can plan for the future and set things up so that the timing of changes kind of lines up with what we want to, how we want to survive. So just knowing how to measure how fast the change happens is very important. This is called the rate problem, which is a very vague problem. Is there a systematic way to figure out how fast things change? It's such a general idea that you might wonder, is there even such an answer to such a question? Doesn't it just depend? I don't know. It matters on what are you measuring? It turns out that the derivative is a generalized answer, that under certain conditions, you can figure out how fast anything is changing with this mathematical tool, which is really crazy that we could even figure that out. And yes, it's in the context someone mentioned earlier of being continuous change. If the change isn't continuous, which some things aren't, then the derivative isn't as useful. But a lot of things from our perspective, they're continually changing, right? Like even if you can't really see it moving, it's maybe moving just by a little bit. So there are a lot of things in life that change continually. Once something is changed continually, and you can kind of figure out a way to measure it by a function, the derivative is how you measure change, period. Like it's the best way. There's no better way. Like that's the game in town, Okay, so that's what the derivative is about, measuring rates of change, how fast something changes. Anything that changes continually and you want to measure how fast it's changing, derivative is the go-to guy. What about integrals? What does that study? Right, so the integral is a useful solution to what we call the area problem. Okay, so this is the study of how to find the area or volume of oddly shaped objects. So you might wonder, why is that a study? Isn't that what geometry is about? Like, I know like the area of a rectangle is this, the area of a circle is that, blah, blah, blah. But the thing is, what if it's not none of that stuff? What if it's a blob? I want to find the area of this blob. How do I find that, right? There's no formula for it. And for every blob, you know how to find the area. Even if you find a formula, there might be some other blob that someone can invent. And now you want to find the area of that, right? This is called the area problem. How much space does this thing take up? So if you want to ask the question, how much space something takes up? That is answered by something called the integral. And it's especially useful if you don't have a geometry formula for the thing you want to measure. How do you go about measuring this? And these two problems are very, very important, literally for the survival of the human race, right? If we couldn't figure out how fast things happen, we'd be dead. If we couldn't figure out how much space something takes up, we'd also be dead. But the area problem is also important for social issues as well, right? So let's say I'm a farmer and I have some plot of land. And, you know, of course, to escape the state of nature, we invent a government. And so the government charges me property taxes for the land that I own. And so they're like, okay, we're going to charge you this much based on how many acres of land you have, right? So here, your taxes are, you know, 15 pence. And you're like, how did you come by that number? Well, we charge you 2.3 pence for each acre you have. How do you know how much acres I have? Look at my land. It's this weird shape. It's not a rectangle. How do you know, right? So how would the government know how much to charge you? How would they measure how much space, how many acres your land takes up if it's a weird shape? If it's a rectangle, it's fine, length times width. If it's not a rectangle, now it's like, how do you know how much you should charge me, right? They had to measure how much space you're taking up to be able to charge you fairly. So, and that is a very big problem because one person might own a plot of land that's a rectangle, another person owns a plot that's a triangle, another person owns a plot that's a circle, and you have nice formulas for all of those. But then you have this guy over here who's being difficult. His land has this weird shape, and you're like, none of these formulas work for this situation anymore. How do I know how much space that takes up? The integral is how you would know, right? So the integral, it starts out very basic. Essentially what you would do is you would kind of slice that thing up into a bunch of shapes that you know what the areas are, and you kind of count that, right? So I know how to find the area of a rectangle. I'd slice these things up into a bunch of rectangles, and then I'd kind of guesstimate the pieces of rectangles. So there's a little piece right here that's not a rectangle, but I'd like guesstimate, okay, that's like a quarter of a rectangle. And of course, if someone is not agreeing with your estimate, what you can do is you slice it up into smaller rectangles, and so you can get the measurement to be much finer, right? But then that and that's the solution to the problem, right? That's a very basic solution. But now you end up in the same situation. Yeah, I could do that for this plot of land, but then what that means is every time I see a new plot of land, I'd have to dice it up into rectangles again. Then I'd have to pay someone to go out and count the rectangles and add them up, right? That's too much manpower, right? So this solution, while it does work, it's very crude in the sense that it doesn't actually give you any sophisticated systematic. It is systematic, but it's not sophisticated. It's going to be a lot of effort to do this every single time you want to measure area. Isn't there a nicer way to just measure area where I could just like plug it into a formula and get it, like pi r squared or something like that? The integral is how you would figure out the formula, right? So that's why the integral exists and why it's important. So calculus is based on these two very important problems. Like, you need to know how fast things are changing. We need to know how much space something takes up. Calculus answers this question in a certain context. Now, calculus as we know it is a little bit different. It turns out that these two things have been studied centuries separately for a long time. These were actually problems that we knew how to solve long ago. Like, we have evidence that Archimedes knew about what an integral is and got very good at computing them, like 400 BC. It's not anything new. A lot of people, though, feel like if you ask them who invented calculus, a lot of people would say Newton, or some would say Leibniz, and that was in the 1700s. That was like 300 years ago. No, the math here has been around for literally millennia, thousands of years. Why is it that Newton and Leibniz, everyone knows them as the inventors of calculus or the father of calculus? Is because calculus as we study it today as a subject is a subject that really realizes that these two things that seem very different, how fast something is changing and how much space they're taking up, they're actually kind of the same. They're two sides of the same coin. These guys are connected by something called the fundamental theorem of calculus. And this is where Newton came in and Leibniz. And actually, Newton's professor, guy by the name of Barrow, he actually invented half the fundamental theorem of calculus. Newton built on it. But the fundamental theorem of calculus realized that these guys, amazingly, you're actually studying the same problem from two different angles. And the fundamental theorem of calculus tells you what that connection is. That connection we only realized 300 years ago, even though we've been doing each thing separately for thousands of years. 300 years ago is when we figured out, hey, you know that dude who's trying to figure out how fast that thing is moving, and that guy over there who's trying to figure out how much space that plot of land takes up? They're actually working on the same problem without even knowing it. They're just working on the same problem from two different angles. The fundamental theorem of calculus is what told us that. And the fundamental theorem of calculus is what's responsible for calculus class, right? So now we kind of figure out, we can actually study one of these problems by studying the other. I can use my insights from integrals to figure out things in derivatives and vice versa. And that realization is what caused calculus as we know it. This is why we're in calculus class. It turns out that these two things that seem to have nothing to do with each other actually have almost everything to do with each other. And there are a lot of conceptual things that we can take from that. A lot of times there are things that you think aren't useful to you, but they turn out useful. So like math class, a lot of people think that math class was a waste of their time, but it's because the world, you don't realize that there's a connection. You've been doing it for a long time, but you only recently, if ever, some people realize that, hey, this is actually useful for this other thing over here. And that's what the fundamental theorem of calculus is about. It connects these two. So that's basically it. Now we are going to start calculus on Friday. I just want to wrap up there. But at the end of the day, I really want you to know what you're doing, why we're doing this, why is it important? It's actually very important. There are two very important things that we need to know how to do. And calculus tells us that we can study one of those things by studying the other and vice versa, and we can get insights from one by doing the other. So what we're going to do is we're going to develop both. Most of our time is going to be spent on differential calculus. Calculus 2 is what focuses more on integral calculus, but I don't think most of you need to take that. So most of our thing is going to be on differential calculus. We're going to build up the tools for that. Then we're going to show that, hey, the differential calculus is actually connected to integral calculus in this special way. We're going to show the fundamental theorem of calculus. Then we're going to spend a little bit of time on the end on integrals after showing that connection. So that's where the class is going. That's what it's about. That's what it is. That's what we're studying. So now if anyone asks you, oh, I'm in calculus class. They ask, what's that? What are you studying? Now you know how to tell them. And they're like, why is that important? Now you know why it's important and you'd be able to tell them. And it's super important, being used in everyday life. And if you use technology, it's being used either for you or against you. And so it's very important for you to understand it. We will get into more applications later on down the road, but that's where we're going. We will end right there. I will see you guys on Friday, where we actually will start talking about limits, where it all began. So we're going to fully understand limits. We're going to use that to develop the derivative, and we're going to spend a lot of time on that. So for now, that's where we are going to end it. So thank you for your attention. Hopefully that was insightful and you kind of know where we're going and why. We will get started on all that on Friday. So unless there are any questions, I will let you guys go. Any last minute questions before we leave? Okay, all right. Yeah, yes. I can't, yeah?
Do we have homework at all?
Yeah, there are a few homeworks that are up already. I think there are about 4 that are already up. I'll be putting up more, but just as a general thing about homework to make sure you guys get it. I mentioned this before, but it's worth repeating. There are 2 major deadlines for homework, right? So one is the week before the first test, and then and that will cover all the homework material that you'll need for all the topics on the first test. Everything else, all the other topics, the homework for that is due the week before test 2, which is when I will test you on all the other topics. So there are 2 major deadlines for homework. That being said, I recommend that you do homework as we're going through topics. So right now you already have homework up for average rate of change, for exponentials, for logarithms. And I would recommend you work on those now. So while you could put everything off to the week before test 1, not recommended. You're going to stress yourself out and it's not worth cramming. So while that is the deadline, you don't have any homework due until like March 16, 17, something like that. I forgot. I would recommend that you do homework for the topics as we cover them in class. So right now you should be able to do all the homework up to average rate of change. And those have been posted. I'll be posting more as we go on because I want to tweak the homework a little bit. But everything that I post is going to be due around March 17th. So nothing due in the near future, but I would recommend that you do it as we're going along. Other questions?
When it comes to like test 1 and quizzes, do you think homework is the best review for that, or should we also do those textbook problems that you outlined in the syllabus?
Neither. When it comes to tests, I will give you the test review and give you more advice. And some of that advice is already on the class webpage. So if you go on the class webpage, you'll scroll down, you'll see a section called Review for Tests. And I pretty much give you instructions on how to review for a test. Homework and textbook problems are important, but that's what you do up until the week before the test. The week before the test, that week, your practice should be different, and it shouldn't be based on homework. It should be based on something else. It should be based on testing, actually, right? So I'll give you old tests to go over, and the week prior to the test, what you should be doing is you should be going over old tests and timing yourself. It's very important to time yourself, right? So the best way to study for a test is to do mock tests, right? The homework prepares you to be able to do that effectively, right? So if you haven't been doing your homework, then you're going to be useless doing a mock test. You're not going to know what to do, right? So you do your homework up until like you try to finish everything like the week before the test, the week, and as in like 8 days out from the test. And then within 8 days of the test, within 7 to 8 days of the test, everything you're doing in that window should be a mock test. You should not be going over homework. You should be taking all the problems from all the topics, putting them all in one so you don't know what's going to hit you, and you time yourself and you do a bunch of that, right? So your practice changes the closer to the test you get. Homework is something you do up until that point. So it's important for preparation, but I wouldn't think of it as specifically test preparation. practicing homework makes you better at homework, right? Practice makes perfect, but practice is specific. There's specificity of practice. You want to get better at tests, practice tests. You want to get better at quizzes, practice quizzes. You want to get better at homework, practice homework. If you're practicing homework in order to get better at a test, you are at a disadvantage. And that's one of the main ways people get into this situation where I'm working so hard in this class and I'm not getting the great grades. How are you working hard? I redo the homework problems all the time. Well, that's the problem. You're getting better at homework. You're not getting better at tests, right? So it matters. I'll give you advice as we go along in the semester, but overall, there are review instructions for tests on the website. For now, I would just follow those. We're not there where we have to worry about it yet. I wouldn't worry about preparing for the test until like the first week of March. For now, just get through the homework, try to keep up with class, make sure you're understanding what I'm doing on a weekly basis, and you'll be fine until like March 7th or something like that. I wouldn't really worry about anything beyond that right now. Other questions?
Thank you.
No worries, no problem. Thanks for your question. So that it, we're good? Okay, all right. If you have any more questions, you'll be able to ask me in the future, of course. We will be spending the next 3 months or so together. So yeah, for now, I'll let you guys go with that. We'll get started with limits on Friday. You can read ahead if you'd like. It'll make class go by a lot smoother. But yeah, that's it for now. I'll see you guys in the next one. Ciao.